All right, I'm going to go ahead and get started. How are you guys doing today? How's the conference been? Lunch work out all right? All right, sorry about the parking situation this morning. For any of you that were affected by that, that was unfortunate. I'm on the board. We didn't know about it beforehand, so hopefully that won't be an issue in the future. I don't know of anyone that got towed. None of you got towed, did you? No? All right, good. Thanks for coming to my talk. I appreciate there's a lot of people here. There's still a couple of empty seats I see in the middle in a few spots, and there's folks standing up on the side, so if you don't mind, try and squeeze in away from the aisle so that people coming in have a spot to sit. And I've got probably a 75-minute talk I'm going to squeeze into a 60-minute format, so I'm going to go ahead and get started. If you want to tweet about this, that would be great. I'd love it. If you tweet with a hashtag up here, improve software, I will look for that afterward, and if I don't get a chance to answer your question here and you don't come down and talk to me afterward because the next speaker needs to set up, I will answer your question on Twitter. I had some Pluralsight tokens. Unfortunately, I gave them all out, so you were lucky if you got one when you got here earlier or sat up front. I have a bunch of Pluralsight courses that mostly relate to software quality topics. The most relevant one to what I'm going to talk about today would be the solid principles of object-oriented design and the way up there, refactoring fundamentals talk. Because a lot of what we're going to talk about today is how you can refactor your legacy code to make it more maintainable and make it easier for you to work with in the future and keep it from turning into a big technical mess. All right, so the big problem with software over time is that it tends to rot. And so all of us that are, I assume, mostly software developers, we've worked on systems, and we've seen that when you first build the application, everybody wants to work on the greenfield project because there's no constraints. There's no legacy code. Everything works. I can do whatever I want. It's so freeing. But then you've got this application that you've been working on for a few years, and it's got actual users that depend on how it works today, so you can't just change anything you want. And worse than that, it's got all the design decisions of either past you or probably worse, past teams that aren't even with the company anymore that made shortcuts and made hacks and made decisions that were expedient at the time, perhaps. But now you're left with the legacy of that software in this legacy software that you have to maintain. And so instead of this finely tuned, oiled machine, you end up with something that looks like this. And this is not what you want to have under the engine of your software. So what we're going to talk about today is how we can do sort of preventative maintenance on our software, just like we change the oil in our cars to keep it running longer. Because over time, software eventually becomes obsolete and needs to be replaced, just like hardware. But because it doesn't have any physical parts that are wearing out, there's no reason why it shouldn't last much longer than hardware that would be doing a comparable job. So one of the concepts we're going to talk about today is technical debt. Most of you have probably heard of technical debt. It's a metaphor for these shortcuts and things in our software. And the thing about technical debt is that you have two components to it, just like with real debt. You've got the actual things that you did or things you didn't do that are accruing as little things you might want to go back and fix. And then you've got the interest on it. And the interest on it is the design decisions and the work you have to do now to work around those shortcuts that you had in there. And so you don't just incur the cost of the shortcut and the fact that you might, in later time, have to go change it. You incur that interest as well every time you make a change. And it takes you a little bit longer because you had to work around that hack or that shortcut that you made earlier. So there's a great graphic I want to show you here that kind of shows how this technical debt applies to your software over time. So on the left here, you've got how much it costs to make a change. Think of this as your time. And then this is how old your application is. And so over time, as your system gets larger, it takes more effort to make a change of unit size, right? That's just because of the size of your application, the fact that it has existing users, you have to have backward compatibility, et cetera. That's all normal and expected. Because you have all the shortcuts and hacks and poor design decisions and things like that, you have technical debt. And because of the interest on that technical debt, it tends to break away from the ideal curve and go sort of asymptotic after some period of time. Your goal is to keep closer to this optimal curve and kind of minimize the technical debt, or at least make sure that when you're incurring technical debt, you're doing it consciously and not unconsciously. You're doing it as a decision that you've decided that we are going to incur this technical debt because of the benefit it gives us of better time to market or something like that, as opposed to we're just coding it like this because it's the only way we know how, and we're going to have to throw it all away and rewrite the thing every few years. All right, so with preventive maintenance in our software, the main thing that looks like is refactoring. And refactoring is how we're going to modify our code so that over time its design stays good or gets better. There's two main things you're going to do in refactoring typically, and those are you're going to eliminate duplication and you're going to try and simplify the design. Now when we talk about refactoring, a lot of times developers think that refactoring is I'm going to rewrite a section of this to be faster. I'm going to rewrite the whole code base to work in an entirely different way. And when I'm talking about refactoring, I'm talking about a very specific thing, which is I'm going to change the design of the code, but I'm not going to change the ultimate behavior of what it's doing. I'm not going to add a feature. I'm not going to fix a bug. And if you're not adding a feature or fixing a bug, you're probably just introducing a bug, which is most of what we do as software developers. So when we're working on this preventive maintenance, the other thing that's important is that we have confidence that the software still does what it did before and that it's still correct. And so it is great if you have some automated tests. You don't have to have automated tests. You could go through and manually test every possible thing that your software did every time you make a small refactoring change, but that is cost prohibitive, and that's wasting a lot of time that, frankly, computers can do a lot faster than people can. So we're going to talk a little bit about automated tests and how we can write our code in such a way that we can run these tests as needed when we're doing these refactorings to improve the design of our code. So the next thing I want to talk about is when does it make sense to refactor? How many of you have ever been on a project and at some point in the lifetime of the project you got the stakeholders, your boss, the project manager, the customer to agree we're just going to stop adding new features and just spend a whole sprint, iteration, whatever you want to call it, on just stabilizing and fixing things. Anybody? Bunch of hands? All right, so probably a 30 of you, great. All right, so that's related to this concept of when should you refactor. And in my opinion, the best time for you to decide that you're going to refactor your code base is while you're still delivering value to the customer. And there's a reason for this. Imagine for a moment that you've got a favorite restaurant. Most of you probably do. And you like to go to this restaurant maybe once or twice a month. One day, you and your spouse or your family go to this restaurant and the doors are closed. And there's a sign on the door and it says, we're sorry, we're closed this week. The kitchen, it was such a mess. We just got to spend this week cleaning up the kitchen. That would probably disappoint you that one time. And it might make you think, what does that kitchen look like that they have to spend a whole week cleaning it up? And what does your customer or your boss think about your code that you have to spend an entire release not delivering the things that you're being paid to deliver, but just cleaning things up? That's crazy. They're probably going to lose some confidence in us as software developers if that's how we choose to operate. And so the best time, I think, that we want to make these changes is as we're adding value. You're fixing a bug. You see there's an opportunity that you could clean the code up a little bit. Do it right then. You're adding a feature, same idea. Another thing that's not related to the refactoring is when you're adding new features, the best way to add a new feature to your code and not break anything is to add it in new code. Instead of always adding a new feature by adding an if check to some existing method and possibly breaking things that we're expecting the old behavior, if you can figure out a way to introduce a new class that just has that behavior and call it from somewhere, you're guaranteed that that new class does not break anything because nothing else in your system knows about it yet. So you're free to design that new class in whatever way you want, and there's no legacy constraints at that point. So think about that when you're writing these new features or fixing bugs. If there's a way you can do it with new code instead of touching old code, that's often going to be a less risky approach. All right. Let me change one thing here real quick. So keep in mind that you shouldn't need to ask permission to do basic hygiene on your code as you're coding. That should be just sort of table stakes or expected behavior for professionals. As you're writing the code, keep it clean, keep the design simple, clean up duplication, all that good stuff. Another principle that many of you have probably heard of that I'm a big fan of is called the Boy Scout rule. The Boy Scout rule for actual Boy Scouts means leave the campground better than you found it. Doesn't mean you have to pick up every little piece of litter that there might be in the entire campground, but if you leave it a little bit better than when you got there, that's making incremental improvement. And if you do that with every commit that you make in your source code, every check-in, you don't have to fix everything today, but if on this commit you've made things a little bit better, over time you keep that technical debt from growing out of control. It's important that when you're refactoring, you're not changing system behavior. I talked about that. There's a way to constrain that, and that's by following this process, which is basically verify what the behavior is today. If it's a legacy system, maybe you just joined the team, you don't even know what it's supposed to do. It doesn't matter if the current behavior is correct. It matters that it's the current behavior, right? Because you're refactoring, you're just changing the design to make the design easier to work with. You're not trying to prove that it's the correct behavior. So if you don't have any tests at all, you're going to start out by writing what's called a characterization test, if you can. If you can't write any automated tests on the system, or you can't write unit tests, you'll suffer with integration tests, or you can't use integration tests, you'll have to make do with UI tests. You can't do that. You'll have to make do with run the thing yourself and make notes, right? And then when you run it again, check your notes and verify it does the same thing. Ideally, it's automated. So your characterization test, you run, and it just verifies, or it just sees what the code does. So if you're writing a unit test, you write a unit test, you say, I assert that when I call this method, it returns, let's say, 0, even though I know that's not right. You run the thing, the test fails. It says, I expected 0, but I actually got 300. You change the test. You say, OK, I expect 300. And now the test magically passes, because you say, I expect what it does. Now you've got a characterization test. You can go do your refactoring. When you're done, you run the test. As long as it still does what it used to do, your refactoring, you're pretty sure didn't break anything with that current behavior. So after you apply the refactoring, you want to just confirm behavior is preserved. So I mentioned the process for the characterization test. Just run it, see what it does, say that that's what it should do, and then keep that as your test going forward. How many of you saw those software craftsmanship calendars that are free out there? If you want, you can pick some up. These images are all from past year's calendars. So spaghetti code is another thing you want to avoid. Sort of an anti-pattern in your code. This is where you end up with all these dependencies, and you start pulling on one thread, and the whole code base starts to be connected because of static methods and other things. So you want to write your code more like Lego bricks than a big ball of wire, so that you can pull out one Lego brick and replace it with another. And when you're working with your code and you've got these Lego bricks, you want to just stick them together gently. You don't want to super glue them so that you can't ever break them apart again. And I've got other talks that go into how you can do that, and most of it has to do with following these next principles, which are the solid principles. Most of you, I think, have probably heard of solid at this point. It's been around for a while. There's one of these that isn't part of the acronym called Don't Repeat Yourself, which I think is the most important one, so it gets position 0. But then you've got the other 5, which is the single responsibility principle, open closed, Liskov substitution, interface segregation, and dependency inversion. So the first one is the don't repeat yourself principle. And we like this principle so much that we included it in not 1, but 2, or actually more of the calendars, which some people thought was ironic. This principle has 2 parts to it. Most of the time we think about it with regard to our code. So if we have duplication in our logic, where maybe we've copy-pasted the same if-then check in a couple places, that is something that we can fix with abstraction. And there's a few different refactorings that you can do to achieve that. You also will see duplication in your processes. So if you have a process where every time after you run this, you have to navigate to the website, hit F5, type this thing into a text box, hit submit, verify that the thing that comes back is correct, and you do that 100 times each day while you're doing your job as a web developer, that is something that you could automate. And so these types of things call for automation if you can do it. Some of the common refactorings that you can use if you're trying to fix repetition in your code are things like replacing magic numbers and magic strings, especially if they occur in more than one place. Replace those with a method or a constant. Parameterizing methods, pulling up fields and methods. What that means is if you've got fields and methods that are in multiple different classes and they all have something in common, you can pull those up into a common subclass that they can all inherit from. You can replace a conditional with polymorphism. This is a powerful technique where you can use that technique I said earlier about writing new code instead of adding another if check or another switch statement. So you could have some code that behaves in a polymorphic fashion, meaning that you operate on a base type, and when you want to add new behavior, you just add a new type, and then have that new type get inserted wherever it needs to be and run that new behavior out of that type. And then lastly, you can introduce a new method if it comes to that, which encapsulates behavior that might be in multiple different places currently. And then you just refactor those other places to all call that method. If you do web forms development, you've probably written code like this at some point and said, is this user in this role? Has anyone written code like this? Have you written it more than once in the same project? Yes, right? So this is another source of repetition that's pretty common. This is something you can achieve some elimination of repetition by changing it and using an abstraction for this. The problem with this approach is that in most of the systems that I've worked on, eventually you end up with something more granular than just admins and not admins when you're trying to see permissions within the site. You know, maybe it's a content system and you've got authors and editors and admins, and now you want to see, well, who has access to edit this article? Well, admins should, and editors should, but only if it's their author that reports to that editor, and the author should, but only if it's their article. And so it's not just as simple as one if is enroll check. And so you want to encapsulate that logic somewhere else, not in your code behind file or in your user interface layer. That's business logic determining who should have access to what. And so this idea of using a privilege as a first-class object in your system is one that you can use in this case. And you know, it's not just for this web forms role check scenario. You can think of other similar authentication or authorization scenarios for regardless of what type of platform you're targeting, where you're doing these same types of repetitive conditional checks, and you might be able to replace that with some kind of an object or method that is a little bit more abstract and is able to pull that logic out of your user interface and into your business layer. There's a feature in Visual Studio that can help you, and there's also third-party tools. If you have repetition in your code, it can identify it, it can find it, it can show you like, hey, this 5-line block of code, it's repeated in 17 different classes. And that can help you identify places that are prime candidates for you to do refactoring and pull this stuff into some more abstract classes or methods. All right, the next principle is a single responsibility principle. The single responsibility principle basically says that your classes should only do one thing, and your methods as well. And so it says every object should have responsibility, and that responsibility should be encapsulated within that object. And more to the point, there should only be one reason for these objects to change, is what Uncle Bob Martin is famously quoted as saying. So when we talk about responsibilities, we talk about single responsibility principle, a lot of developers aren't familiar with what is meant by this. Like maybe you've got a customer manager class, and the customer manager only has one responsibility. It just manages the customers. That's what it does. You know, it gets them from the database, and it validates them, and it makes sure that they can place orders, and it does those things. But it's just for customers, so it's one responsibility. So let me spell out, you know, what are some of the things that are responsibilities. Here's the customer manager one, right? So examples would be things like persistence, validation, error handling, deciding which objects you're going to collaborate with, doing logging, doing formatting or parsing, notifications can be another one. Any of these things could be considered its own responsibility. If your class is doing several of these things all together, it might make it so it's more difficult to maintain, and you might benefit from doing some refactoring that breaks apart those responsibilities. You might also find in some of these cases, these are cross-cutting concerns, like logging or error handling, where you're trying to do the same pattern throughout your code base, and you end up doing the same blocks of code across many different objects. If you can find a way to pull that into one location, you'll cut down on a lot of repetition in your code as well. One of the things you want to look out for in your code is tight coupling and too much dependency. It's ideal for you to have loose coupling between your systems and the places where you want to break them apart. This makes it easier for you to test things. It also makes it easier for you to introduce new behavior to your system in a way that doesn't require you to change the existing code. And that's another principle I'll get to in a minute called the open-closed principle. Some common refactorings to keep the single responsibility principle, if you find that it's being violated, are extract class, extract method, or move method. Basically, if you follow this principle, you'll probably find that you're going to have more classes, but they're going to be smaller, and they're going to be doing one thing, and they're going to have a real strict focus. Another useful tool in Visual Studio and other places are some of these heuristics. So one of the heuristics, the most important one, I think, is something called Cyclomatic Complexity, which is this one right here. So this is an example of a code kata called the Gilded Rose kata. It's a refactoring kata. You can find it on GitHub and just about every programming language out there. And it gets, unlike many other software exercises or katas that say, hey, go do this set of steps and write tests or whatever, this one gives you code to start and says, here, add this feature to it. And the code has one giant method that does most of the work. And in this case, what the work is it's like a World of Warcraft store with a bunch of items in it, and every day the value of the items changes. So there's an update quality method, which is this one right here, and it does all the work. and it has a cyclomatic complexity of 19, and it has 28 lines of code. Doesn't sound too bad, right? Well, if you look at it, it's nothing but a huge nested if, then, else, if, else, if, else thing that when you are then given this task of adding a new type of item that has its own logic for how its quality updates, it's a little daunting at first. And there's no tests. That's part of the exercise. It's, hey, maybe you could write some tests. What cyclomatic complexity is simply a measure of how many pathways through the code there are given all the different possible conditionals. So if you have a method that just returns something, it has one possible pathway through it. It's got a cyclomatic complexity of 1. If it says if something, do this, else return that, it's got 2. So you can see 28 is, 19 is the cyclomatic complexity for this, is pretty big. There are lots and lots of code bases out there where this is a drop in the bucket, and you'll see cyclomatic complexities that are much higher. In addition, Visual Studio also has given you these other measurements like class coupling, depth of inheritance, lines of code, and they have their own aggregate thing, which is their maintainability index. Their maintainability index goes up to 100, which is great. And then like 44 is pretty abysmal. But hey, Visual Studio still think that's green, right? I don't know why. So it'll go down to 0, which it'll actually say, oh yeah, that's bad. But really, you don't want to have something that's a 19 in your code base if you can help it. In fact, if you go out to Wikipedia and look at the cyclomatic complexity thing, it'll say cyclomatic complexity should not exceed 10 in most places. It should be pretty rare that you're going to see something over 10. So again, if you're looking for places in your code where you could do refactoring, look for these heuristics and identify the methods that are really long, that are really complex, and see if you can break those apart. And try and keep cyclomatic complexity under 10 for every method. Now in this chart I just showed you, it will roll this up to the program level, the class level, the namespace level, and cyclomatic complexity just sums up all those things. These numbers are meaningless, right? It only matters at the method level. So another useful technique is if you're using this tool, you can export it to Excel and then filter in Excel so that you only see methods. Because you don't care about what the complexity is at the class or the namespace level. It doesn't matter. Here's an example if you do export it to Excel. This is from a client I worked with where maintainability index really does go to 0. Cyclomatic complexity 394 for this method. There's 394 different pathways through one method. How are you going to maintain that? How are you going to have any idea what it does? There were no tests either. So this is the type of code that we're talking about that's out there that you want to try and fix. And it's only 1,300 lines of code for this method. All right, it's no problem. All right, another quick code smell that you might see. When you have a really long method, one of the things you can do if you don't want to mess with it because it's scary, you don't want to actually refactor the thing because you don't have tests, is you could just put regions around it and hide all the scary parts. And so you end up with things like this, where you've got this region where you say, oh, I've got this method and we'll do all these things, and hide all the code in regions. Regions are like carpets under which you sweep stuff you don't want anyone to see. And they're especially bad when they're in a method. So I'm not a big fan of regions. I think regions, they served a purpose when .NET first shipped because we didn't have things like partial classes that let us put generated code somewhere else other than our class. Now that we have partial classes and all the other features, there's not a whole lot of reason why you need them. And it's really frustrating for me when I'm trying to go look at a class and it looks like this. I'm like, what does this do? I have no idea. And I go into customers sometimes, they have a policy that every class will look like this. 4 of those might be empty, but my gosh, there's going to be a region there just in case someday we want to put it there. I would rather the classes be so small that when I open it up here, I can see the whole thing at a reasonable font size. All right. So now let's talk about the open-closed principle. And the open-closed principle, basically, in here it says, brain surgery is not necessary when putting on a hat. The idea with open-closed principle is that you should be able to change the behavior of something without having to go in and do surgery on the inside of it. So you should be able to change behavior without having to change the internals of it. You don't have to rewrite the code or recompile it or redeploy it. You should be able to do it from the outside. So open to extension means you can add the new behavior in the future. Closed to modification means you don't have to modify it or you don't have any way to modify it in some cases. Quick example of the open-closed principle. Here's some different refactorings you can use. I'm going to skip past these. Quick example is imagine it's a few years ago and Windows or whatever you're using doesn't have an automatic photo import. So you're going off to somebody's blog. I actually had a script on my blog at one point that did this, where you can plug in your USB thing from your camera or plug in your camera on a USB cable and it'll suck all the things into a folder for you. and maybe rename them all and put them in appropriately named folders, which of course the only appropriately named folder for developers is going to be YYYY-MM-DD so that they all sort correctly by date, right? So if I had this on my blog and I made the exe available as a download, what are people going to say when they try to run it? Especially non-developers that aren't going to crack open the code and rewrite it themselves. What? Yeah, the directory doesn't exist, or let's say it's going to make it, right? But it's going to be in Steve's photos. So I've got a handful of my users that are going to be named Steve, because oh my gosh, Steve Smith is like the most popular name in the world. But most of them are going to be like, why is it always going in Steve's photos? And so this is something where if you're a developer, no problem. I can grab the source, I can change that line of code, or I can put an if statement, or I can do whatever. But it's violating open-close principle. You have to go in here to change the behavior. You should be able to change the behavior of this code without having to go in and actually change the code itself. And so one of the easiest way to do this, as you saw in the refactoring bit, is just introduce a parameter. And so if I made it so that the user could pass in a parameter that said, hey, which folder should it go to? Now I'm following the open-close principle. And it can be as simple as that. In many cases for our classes, instead of it being a parameter on a method, it's going to be a parameter on a constructor, where we're going to be able to change the behavior of a class by passing something into its constructor that it is going to use to do whatever its job is differently, or to collaborate with different sets of objects in our system. Another example is where you've got some rules in your business, and over time the rules keep coming, right? So initially, the business people come to you and they say, we want to offer a special discount for people that live in this region. And then they come up with another region, and another region, and another rule, and another type of special case. And so eventually you've got this method that looks like this, where every time they come and they say, you're like, no problem, I can if statement that. And you write another one. This code gets more and more difficult to test and more brittle and likely to introduce bugs. So this is another example where you can see the writing on the wall, right? When you come into this method for the 7th time and you're adding yet another if statement, you should be thinking, this is violating the open-close principle. I keep having to change this method because the business conditions and requirements keep coming, and I keep having to update it. So a refactoring you can do here is what's called a rules engine. And rules engine sounds kind of scary. It's like, oh, that's like some enterprise software package I'm going to have to spend, or there's some Microsoft thing I'm going to have to go spend a week of training on. But it's really not that difficult. So you can create a simple rule interface that might have like one method that says, apply this rule, or say whether or not it applies to this particular thing. And it only takes you a few minutes. And then you can write an individual rule for each one of those different conditions. So in this case, I've got are they a special customer? That's my interface. And then I can have a bunch of rules and say, evaluate this customer. And if it's false, then I'm going to return false for whether or not they're special, right? And so you can change the logic depending on how you want to implement your rules engine. Sometimes your rules engine will just have one method that's like a Boolean, like this one. Other times maybe it's doing some work, and so you'll do the work on whichever one, and like maybe it's calculating their discount. And they might be, they're a veteran, and they're over 65, and they're, from Litvonia. And so that might authorize them for 3 different deals. You want to give them the best deal, so you have to calculate all their discounts and return the best discount. That kind of stuff is very common, and you can achieve it very easily using this type of system. And if you want to learn more about that pattern, there's a whole thing on it on Pluralsight in their design pattern library. So then Liskov substitution is the L in solid. And Liskov substitution here in this example, it's talking about if it looks like a duck and quacks like a duck, but it needs batteries, it's probably not the right abstraction. And what Liskov substitution says is that your types need to be substitutable for their base types. How many of you, when you learned about object-oriented programming for the first time, you learned about inheritance and this relationship between the base type and the subtype? What's that relationship? Anyone? What's this blank this? This is a, right, yes. So everybody hears about the is-a relationship. What this principle says is that is-a is not sufficient. Right? It's required, but it's not sufficient. It's not just that it is this, it's that it's completely substitutable for this. And so if you have situations where you can't use this thing as this base type, it violates this principle. And I should mention, with all these principles, this doesn't mean you have to always follow all these principles all the time for all your code. These are all things that you want to address when they're causing you pain. So I call it pain-driven development. So if these are causing you pain, you could think about these principles and use them as a guide to alleviate your pain. All right, but don't try and code up everything to follow every principle from day one. Like, you cannot follow open-close principle with every method from your code from the start because you don't know what changes are coming. You can't anticipate what the customer is going to want to change. So if you abstracted out everything completely, your code would be, wouldn't do anything. It'd be unusable. So Liskov substitution, you don't have to write like this from the start, but if you start seeing these types of code smells I'm about to show you, you can think about, oh, this is probably violating Liskov substitution. I could fix that. So common refactorings for this are to collapse hierarchies, pull fields up or push them down. Basically take your inheritance hierarchy and squash it down somewhat or move things around so that they aren't violating the principle. An example is when you see polymorphic behavior. Polymorphism being where you're going to work, let's say, on a collection of some type, and you don't care whether it's that exact type or a subtype. So in this example on the board or on the screen, you see like employees. They're all of some type of employee, right? But in one case, I'm going to say, wait, no, if this type is type manager, which is a subtype of employee, then I'm going to call this special helper method to print managers. Otherwise, I'll just print the employee, right? And the problem with this type of code is if you're only doing it in one place, that's fine. But this type of code tends to start to spread throughout your code. Anywhere you're doing something with all the employees, now you're going to maybe have to do some special case for that one type. And so you start violating don't repeat yourself, and you start introducing bugs where you fixed it in two places but not the other, and now things don't work the same in two parts of your system. And these are hard to track down and easy to introduce later as regressions. So the fix for this would be to change this so that the behavior is encapsulated in the class itself, or you write the helper method or whatever's responsible for doing the work in such a way that it can handle any of these base types and achieve this. Another thing to remember is that if you're writing code that has a lot of null checks, the checking for null is basically a Liskov substitution fail most of the time. Like you're having to do something different because it's not the type you expected. I expected an instance, and I got a null. And so I have to check for that and I have to do something different. You can fix the checking for nulls everywhere in many cases by using what's called the null object pattern. So that when you get something back and it's not found, or it's not there, or it's not created yet, or whatever the reason is that it's null, you have a special instance of that object that has all the default values so that you could print the thing that you were going to do here. You were going to say not found. You could just print an employee whose first and last name are not found, right? And that could be not found employee. It could be the name of the instance. And you just return that. And if you have that instance, this if check doesn't have to be here, right? You just print it like you would anything else. And so now your code's complexity just got a little simpler, and you're not having to do these checks as much. And you can test that everywhere in your system when there's a not found, you do the same thing. So your code gets a little more consistent as well. Next, let's talk about interface segregation. So in this example, we've got our iPod or iPhone here and headphones with an interface that can work for any type of audio device, right? We don't have actual devices that look like this because that would suck. And so instead, what we have is something that works with the most common thing that we're typically going to use, and we have these little adapters. And there's actually a design pattern in our software called adapter, and that's what it's for. So you can actually, if you need something that plugs into different things, you just write the adapter you need and use that as a bridge between the two systems. So the interface segregation principle basically says that your clients should not depend on methods or behavior that they don't use. And the corollary to that is that you want to have small, very focused interfaces, not really fat interfaces. So the most common refactoring for this is to extract out an interface. So how many of you have worked with ASP.NET? Very many? How many of you had to work with a membership provider in 2.0 days? How many of you had to write your own membership provider? All right, now for real, keep your hands up, everybody that did that. How many of you implemented every method that the membership provider exposes? Yeah, like maybe one, okay. All the hands kind of like, All right, so this is the membership provider. This is like the biggest violation of the interface segregation principle because this is 17,000 methods that the membership provider requires that you fill out. And most of the time when you're building an ASP.NET website, you need like 4 of them. You're like, I need to log in, I need to create a user, I need to forgot password. That's it, right? And you don't need all the rest of this stuff most of the time. But if you write a membership provider and your system is expecting it to be there, there's various controls and other things in ASP.NET out of the box that expect that that provider is going to support various parts of this interface. And so if you bring on, let's say, a new developer, and they're tasked with adding some feature, and it happens to use one of those controls that expects this provider, and you've got a not implement exception in there, they're going to have no idea until they're almost done with the work, and they go to run it, and it just blows up. Because your interface, that's a Liskov substitution fail, by the way, but your interface was so fat that you didn't want to implement all of it. You only needed a subset. The other problem with that approach is that, in this case, the framework is defining this massive interface, and the client, which is your one page in your web form, or your one controller in your MVC app, or whatever it is that you're writing, that client object only typically needs a handful of methods, maybe 3, let's say. It doesn't need all of this. And so what you want to do is write an interface that the client owns, that the client has control over, not necessarily in the UI layer, right, but it's in your solution. It's like it's an application level interface that you control and you own and you write against. And then you write an adapter or an implementation of that interface that's going to work with whatever the underlying functionality might be, whether that's auth0 or membership provider or what have you. Here's an example. The repository pattern can be an example of an interface segregation principle failure, because in many cases it has all these methods for doing a get, a list, an update, a delete, an insert. And a lot of times you'll have a page or a form or a controller in your application that only needs to do some of these. Now, you might think, well, this all makes sense because this is all related to one thing. This is all data access, so it's fine to put it all together. But in some cases, you're going to want to implement these things differently, because you might have a system where, for scalability reasons, you want all your writes to not immediately call the database and block on the database operation before returning to the user. Instead, maybe you have this CQRS, command query responsibility separation that you're doing. And so you want to queue up all the writes that you're going to do and do that instead, right? And eventually they'll end up with some other process writing them to the database, and you'll get that eventual consistency. But you don't want to do it right then. But maybe you're getting your list, you still want to talk to the database directly, let's say. Or let's say you've got a different problem and your gets and your lists are slow, and you've got a website that's mostly content that hasn't changed, so you want to introduce caching. But you don't necessarily want to cache your update and your delete statement. I mean, yes, they may want to do something like delete the cache when they occur, but let's say you've got that covered through some other mechanism. You don't need to write an interface that does caching that includes those methods. You would just have non-implemented exceptions or something for those. So a cool thing you can do, if you've got a fat interface already and you want to break it up, and I'm not saying you have to do this with all your repositories. Again, pain-driven. If there's a reason to do it, you might do it. But in your own interfaces that you have today that you find that are too big and they're causing you some pain because of that, you can actually use this interface inheritance feature of you get multiple inheritance with interfaces so that you can break them up into these smaller 2 interfaces, read and write, and the original interface is preserved. Anything I had that was depending on this interface is not going to break. I'm not going to have to recompile it or anything when I replace it with this one, because it's still the exact same interface down in the .NET internals because of the fact that it's inheriting the same structure. But I can write new code now that only uses these more finely grained interfaces without breaking any of my legacy code. So this is another important technique to remember. If you've got interfaces that are huge and it's causing you problems trying to work with them, you can break them down and keep your big ones where they are so you don't have to change everything that depends on them today. All right. The last of the solid principles is the dependency inversion principle. Dependency inversion principle is one of the most important ones. This one says, would you solder the lamp directly into the electrical wiring of your wall as opposed to having some kind of a plug that you can use as a common interface for power on your apps? Dependency inversion principle basically says that your high-level modules should not depend on low-level modules, but they should depend on abstractions. And when I talk about abstractions in C#, in .NET, and strongly typed languages, I'm talking about interfaces and abstract types. Furthermore, abstractions should not depend on details. They should, the details should instead depend on the abstractions. So how would an abstraction depend on details? Well, let's say that I've got that repository interface I just showed you, but instead of returning back a list or an enumerable or something like that, it returns back a SQL data reader. Well, that interface now depends on system.data.SQL client, because that's where SQL data reader lives. And it depends on SQL Server. It depends on all kinds of details of implementation. I can't return it from a file system now easily because I've baked in that detail into that interface. So you want to keep your details at the plain old CLR object level where they're not dependent on a particular implementation detail of how you're going to get the data or how you're going to do the operation. So depend on abstractions. You want to inject dependencies into your classes. Most of you have probably at least heard of dependency injection. I'll talk to you a little bit about that before we're done. And if you can, you want to structure your solution in such a way that all your dependencies are flowing toward your business layer, which I call the core in your application, instead of flowing toward your database. So when I first started speaking, which was back in 2001, I did a talk where I showed this N-tier development. And this is what Microsoft had on MSDN website at the time. And these are like the different ways that you could write software. And separating things into layers was kind of new at this time, because everything was just like, hey, it's a VB6 app, and it does everything in the click behind, of the button. So this was progress that we were getting to this tier layer system. But the problem with this approach that is still widely used today is that all the dependencies point downward to the data source. Like the arrows go both ways because data flows back up, but your dependencies all go down. Oops. That way. There we go. And that's bad because now it means that your tests and all the code that you want to write to automate things is very difficult because you're depending on the database. So real quick, I want to jump through some data access talk that goes along with what I just showed you. So in the early days, when you'd write your data access code, you'd have, say, a button click handler or whatever, and it would open a record set and immediately do the work on the database, and there was no separation. And you would have these two behaviors, one at compile time and one at runtime. And they would be identical, right? Exactly how you wrote the code and how you compile it, that's how it ran. And then later on, we would get, in like 2005 era, we'd have all these helpers, like the system dot, what's it called? The SQL data helper. Data access application block, that. And the helpers were nice because they cleaned up a lot of the duplication. I didn't have to open a connection inside of every web form. I could do it all with just this SQL helper. And so that was nice, but it just still made the dependencies go the same way, right? My runtime and my compile time dependencies still were parallel and following the same path. So the missing thing here is this abstraction where instead of depending on the details, instead of depending on the database, I'm going to depend on an abstraction that's coming from somewhere else. And so what I'm going to call that abstraction is a repository in this case. That's the common name. And not having all that stuff led to these tightly coupled kind of big ball of mud systems that would be very difficult to change over time as they got bigger. When you've got the repository in there, though, you can swap that out with anything else you want. You can swap it out with an in-memory solution. You can swap it out in your test with some kind of a mock or fake that just gives you some data without you having to set up a test database, which is painful and slow. And so the way this works is that now when I compile the code, I'm going to follow the blue arrows. I'm going to have this core project in my solution that defines an abstraction. It defines a repository, just the interface. And my user interface at runtime is going to use an implementation. And an implementation might be for whatever type of infrastructure I want. Today it might be the SQL foo repository. Tomorrow it might talk to an XML file, or it might talk to Azure Table Storage. I can swap that out. And because of this design, I can swap it out without having to change anything in any of these existing pieces of code. Right? I'm going to write a new class that does that new behavior, and there's no way I'm going to break any of the existing behavior because it doesn't exist yet. Right? So it gives you that way to add this new functionality in a very risk-free way. So this architecture that you'll follow if you want to do this is called the onion architecture, or Uncle Bob is taken to calling it, I think, the clean architecture now. It's ports and adapters, hexagonal. Yeah, it goes by a lot of names. But the idea is that you put your domain logic, your business logic, in the center of this core. You put your interfaces and your abstractions in there as well. And you put the infrastructure and your services and your user interface outside of that, kind of pointing toward it. And your core has no dependencies. So everything in the center of your application, all your business logic and your model of how the system works, is extremely testable. It's very fast and easy to test because it doesn't depend on anything. It doesn't depend on your network, your file system, your database, none of that stuff. And that makes it really nice. It makes it fun to write code because you can write these tests for all that stuff and not feel constrained about all the legacy of all the dependencies that your code has built up over the years. Common dependencies that you'll have, some of these you can't avoid. You're going to depend on a framework. You're writing .NET, let's say. You're depending on a .NET framework. You're writing for Java. You're depending on their framework. You're not going to get away from that. But most of these other things, like third-party libraries, the database, the file system, you're going to want to write to an interface or an abstraction and not write to it directly. And some of these you don't necessarily think of as being dependencies until they bite you. So, for example, you've got the system resources like the clock. If you've got somewhere in your code that says, well, if daytime.now, whatever, it's between 8 and 5 on a business day, I'm going to do this, otherwise I'm going to do that, how are you going to write a unit test for that? Your test is going to run and it's going to be successful during the week and it's going to fail on the weekends? That doesn't make much sense. You're going to have to alter the machine clock on the test server. That's not going to be good. So Even things like that you can abstract. You might have code that has random logic in it. I wrote a server that served up ads to developers like you back in the day, and I had to show up a random ad, and it had to be weighted so that over time each of the ads got the right number of impressions that they had paid for. Well, I wanted to test that, and it's difficult to test random code. You're like, well, I'm going to hit it 1,000 times, and I should get about this many back, right? And those tests would fail sometimes because random. And so you can take random stuff and write tests for that if you've got an abstraction where you can introduce in your test and say, okay, random, in this case, is 4, right? I'm randomly deciding that it's 4 for this test case, and you can do that. Same thing with thread sleep. If you've got real legitimate reasons to have thread sleep in your application code and it's slowing down your tests, wrap that up in an interface, I sleep or whatever, and then in your tests, if you don't need it, just make it do nothing, just no op. And now your tests are going to go much faster. You don't have to wait on thread sleeps in your test code. Also, all the responsibilities I talked about with SRP are things that you might think about as dependencies. So common refactorings for this are extract out classes and interfaces, apply the strategy pattern. If you look up the strategy pattern, if you're not familiar with it, that is dependency injection. So they're the same thing. So if you learn about the strategy pattern, you'll know how dependency injection works. Extracting methods and introducing an IOC container or service locator can also help as well. A couple examples, and I'm about out of time, where this fails. Here's an example where you've got some tightly coupled code that sends an email. And with a little bit of refactoring, I can change this to use a helper. So now the method is a little simpler. And with a little more refactoring, I can extract out an interface, put an implementation here that does the actual mailing, and then pass that in. So now the cart that does the checkout is going to be just something that calls the thing that was injected to send the mail. And if I want to send a mock object or something in that, I can very easily. All right. I am out of time, so I'm going to end it here. And thank you very much for your time. I'll jump up to a thank you slide. There we go. Thank you very much. And if you have any questions, feel free to come on down. I've got a couple minutes, but the next speaker needs to get set up as well. So. Do I have 15 minutes? Oh, well, never mind.
I was going to give you your attendance.
Oh, I saw you coming over.
No, I was going to go give you.
Hey, I got more time. I'm sorry.
Okay.
As you were. That's good, because I thought I had more time, and I was like, whoa. All right. Sorry. My bad.
Were you in the Army?
I was.
I
As you were?
Yeah,
Yeah.
as you were. I heard
Yeah.
that. I was like, oh, we're the only people that say that.
I know. All right. That's good, because I wanted to cover this important thing. So if you're tired of what I was talking about and your code is great quality, go ahead, move on. There's snacks and beverages down at the end of the hallway, which is another announcement. So there's like 1,000 cans of pop still down at the end by Theater 11. Feel free after this to go grab some. And before the movies, you can go grab some there. That's where the popcorn will be, too. And so what do I have? I have now like 11 minutes or so. So we're going to talk about something that's important to me, which is how we can improve quality throughout the industry. And so first, let's talk about how we write good code. And I found this cartoon, this flowchart, and it kind of applies to a lot of us in terms of how we think about writing our software today. Does this seem familiar to many of us? So the challenge is that we often come into this iron triangle of you can have it fast or you can have it right. Pick one. Right? And the iron triangle in software is fast, right, and cheap. Right? You can pick two. Like one of them has to vary. And as software developers, we can kind of vary the cheap one, because if we're able to deliver it fast and high quality, our rates get to go up. We can go find a better job. So we can improve on the cost factor for us. But in particular, when we talk about how we're writing our software, if we do find that it's true for us that we can write code in what we don't consider to be a good way quicker than we can write code that we do think is quality code, we want to try and fix that. And the way we can do that is by practice, by learning, by coming to conferences like this, by learning these techniques that we're able to write code as close to a good design at first, and in a way that is easy to change. Like, I'm not saying that when I write code, it's perfect the first time I write it. It never is. That's why I spend all this effort on refactoring. It's because I know I don't know everything when I write the code. I want to be able to change it later. So I'm going to write it in a way that I can change it later. And I'm going to spend some time practicing how to change it so that I'm pretty good at that, so that I can evolve my code over time. And it can grow as my understanding of the problem grows, and as the customer who keeps changing their mind, their understanding of the problem grows as well. So let's talk about how we can change the output level that we have when we're writing high-quality code so that it is better and higher and closer to the output level we think that we have when we're writing crappy code that we're just spitting out as fast as we can. So here's sort of a graph where the high quality is blue and the low quality is green. And this is what most of us, if we were to say, raise your hand, yes, I can write poor quality code quicker than I can write good quality code to solve the same problem, right? To complete the same behavior, the same user stories, I can churn it out with crappy code faster than good code. And I think that most of us would agree. How many of you would raise your hand and say, yeah, that's probably true for me? Right? That's like 99% of developers, I think, would raise their hand for that. I think, for me, I think it's pretty close. Right? I think I'm close to the point where I could say I could write code that's high quality as fast as I can write crappy code. Because it almost like pains me to write crappy code at this point. And if you go and listen to Uncle Bob Martin speak, he's written a bunch of great books like Clean Code, and he's the one that came up with those solid principles, or at least compiled them together for the first time in one of his books. He says, he's totally over the line, right? It's like, I can write good code faster than I could, write crappy code, because he's going to write it, he's going to write the tests first, he's going to make sure that he's making incremental progress as he goes, he's going to refactor as he needs to, and at the end of the day, he's not going to get mired down in bugs because he didn't have the tests, or in having to change his design but not being able to easily because he's used a tightly coupled system that's not easy to refactor now, and something changed and he has to make a change, or now we have to code around it for the rest of the life of the application. So we want to get to the point where we can consistently just write the higher quality code as fast as we can write lousy code. And that's sort of our challenge in the industry. That's what I want you to take away from this talk is think about the techniques that I've covered today. Think about some of these principles and look in your code for places where you can make the code a little better each time. Look for ways that as you make each commit, you can improve that code so you don't have to worry about having to clean it up later. But it's as good as you can do it right now. And you might find that it takes you a slight amount of time more in the early days. It might even take you a significant amount of time more, but your code is going to have fewer bugs, and it's going to be easier and cheaper to maintain just by virtue of the fact that you're writing that better code. And resist the temptation or resist the pressure that is coming from management or from your peers to just churn out crap as fast as you can. Ideally, you're a collaborator and a team member where you are bought into the needs of the system. You understand the business value of what you're building. And so you could make the decision or be part of the decision to say, in this case, it just has to get out there fast because StirTrek's tomorrow and we need a demo at the booth and it doesn't have to have 100% test coverage, right? In that case, it might make sense to just code up something that you can throw in a booth demo. But if it's getting checked into your actual product and you're going to have to support it with real customers for years, you probably are going to be better off to spend a little bit of extra time and make sure that that code is a little bit better when you check it in. Follow the Boy Scout rule. Make sure that you're leaving the code better than you found it with each commit that you make. And over time, instead of your code collapsing under its own weight, it's going to live a little bit longer, and you're going to be happier working on it. All right, so that is actually the end of my talk. I have a summary slide here. I have some more resources on the next slide. The key takeaways for this are the solid principles, dry, refactor as you're adding value, not in like a big bang approach with a whole iteration devoted to it. Don't change behavior when you're refactoring, but just keep the behavior that's same, but clean up how you're doing it. And figure out ways that you can start to write good code as fast as you write code that you don't think is high quality, in your own opinion. Thank you.